Welcome. My name is Perry Dugutla. I'm based in the South African office. So, welcome to our session today. The topic for today is resistance, spot welding, and multi-material automotive design. This will be presented by our Dr. Ariventen Arumagam. For sure, I said that correctly, Doctor.
Okay, you can just simply call me Arvin. Everyone in EAT calls me as Arvin.
Oh, okay,
Yes,
all right.
it's just just Arvin. Yeah.
Yeah, okay, all right, no worries. Yeah, just ensure that you disable all the settings. And just for those who are actually joining us for the first time, so these are just common questions that we normally get during the session. People want to know about the slides and the video certificate of attendance. So just note that within 2 business days, we will be sharing PDF slides and also a link to the recording for this session. And then once again, the certificate of attendance, it will be sent to you only if you have completed the short survey form, which I'm going to provide you with the link or the QR code at the end of the session. So just ensure that you follow the link and then just complete the survey and send it through in order for you to get the certificate of attendance. And then just to give you an overview for those who are joining us for the first time, so EIT, engineering specialists, we specialize in the engineering programs. So our courses starts from micro credential courses. You've got our advanced diplomas, undergraduate, graduate certificates, bachelor's degrees, masters, all the way to Doctor of Engineering. At EIT, we are industry orientated, so we ensure that all our materials, all our resources are up to date. As you can agree with me that job market is now changing, so we ensure that our materials too, as well as resources that we use for students, are up to date to keep up with the trends. EIT is just like any higher education provider in Australia. We are accredited with Australian government. We also have our programs that are also recognized under 3 international accords, which is Sydney Accord, Washington Accord, and then you also get Dublin Accord. And then, we've got our lectures from different parts of the globe, and we use unique method of studying. They use live and interactive webinars for our students. And I'm just gonna quickly hand things over to Doctor. If I can just quickly share your
Okay.
slides, just a
And this is being
moment.
recorded anyway, right? So I can see the recording icon anyway. Because
Yeah.
yeah. Okay.
All right.
All right. And I can obviously unshare this and share my presentation slide, right? Once I'm
Um,
done with this.
actually,
Yeah.
yeah. I'll do
Yeah.
it
All
on
right.
my end. No worries then.
Okay. So you got it on your end, yeah? All right. Okay.
Yeah.
The revised version, Barry?
Yes, it's loading now.
Oh, okay, all right. It's like if you can just leave that the introduction part, because I did not have the introduction slide in this one. So you can just leave that once I finish my
Mm.
introduction, and then change that to the presentation slides.
Okay, no worries.
All right. Hello, everyone. First of all, let me have a quick introduction about myself, and then we can carry on with the webinar content. All right. I'm obviously keeping an eye on the chat, but I can't see anyone. Okay, yes, I can see that now. All right, great. All right. Welcome everyone to this webinar. In fact, I've been with EIT since 2019. I would say that this is pretty much the first time I've actually got the time to do a webinar. So it's more for EIT is my very first webinar. But let me go straight into the typical introduction. My name is Aravindan Arumugam. All right. You can simply call me Arvind for this 1 hour. You can simply call me Arvind. Now, I mean, originally I am from the beautiful city of Kuala Lumpur. I'm a Malaysian. All right, so I'm not sure how many of you are from that part of the world. All right, so I'm actually from Malaysia, Kuala Lumpur. If you know where exactly whereabouts is Malaysia, closer to Singapore. All right, so so after that we've kind of moved to Perth. So I'm currently based in Perth. That's when I joined EIT. This is way back in 2019. I've joined EIT as the unit coordinator, and I'm also the discipline head for the VET programs under diploma of advanced diploma of mechanical engineering, as well as advanced diploma of mechatronics engineering here at EIT. Right. So and usually the topics that I teach would be more on engineering mechanics. My background is mechanical engineer, hence it's quite natural that I'll be teaching more of the units relating to mechanical engineering. So I do teach engineering mechanics, physics for engineers. That's a unit that I'm currently teaching. I do teach pumps, compressors, and turbines, and obviously under VET, the vocational training here at EIT. I teach numerous various subjects relating to the field of mechanical engineering. Right. Now, my PhD is on resistance spot welding. So I would say that I decided to start my first webinar with my area of research and area of expertise. So I've been obviously working with this welding process for quite some time. All right. So I graduated with a PhD in this one, and I'm also currently doing a research within this particular area, because the spot welding obviously looks like a very simple process, but to be honest with you, there's a lot of things to look into in this one. A lot of things, even though it looks like a very simple process. I'm hoping to give everyone here some insights of this in this webinar today, and obviously hopefully there's something that you can take away after I've completed my webinar today. All right, so saying that, let's go straight into the content for today. Now, we'll start off with an introduction on resistance welding, and then we'll go straight into the resistance spot welding process, a process that has been is one of the oldest welding process, I would say, even way before arc welding came. All right, so it's a very old welding process. We'll talk a bit on the introduction part of it. We'll look into the parameters involved, the quality aspect of it, and so on and so forth. No worries. And then after that, we will go into the concept of material design, multi-material design, automotive industry. It might look as if it's two different parts. In a way it is, all right? But then I've merged that together, because one important point when it comes to multi-material design in automotive, or simply I'll just call that as MMD for now, right? That's way easier to say. Okay, so in automotive, MMD, the multi-material design, is obviously an area that's kind of picking up. And since resistance spot welding is one of the important welding process in the automotive industry, it's going to be natural that you can easily link them together, right? So we're going to go through that, and then I will look into some challenges that we are currently having with regards to resistance spot welding, and welding some of these new materials that has came up in the past decade, right? Thing that's the AHSS, the advanced high strength steels, and then we've got the composites and the light alloys like aluminium, magnesium. Obviously, titanium is there, but I'm not going to cover titanium, right? So we'll look into each one of these. So the intention of me in this webinar today is to just go on more of a basic level kind of a thing. I'm not going to put into any of scientific jargons and in terms of metallurgy and all kind of things, and which might end up confusing people. Once I finish this, I will check with you guys what is your at least prior knowledge on this thing, so at least I can gauge my the audiences that I've got, and I can kind of manage my information a bit more easier. So it won't be too much detail because we can't go into too much detail. We need to talk about too much into the aspect of metallurgy. All right, we need to talk about things like all this austenite and martensite. I have to, in a way, have to say that, but we won't go too much into all these equilibrium phase diagrams and stuff like that, which is directly related to why these challenges are there in the first instance, right? So we'll cover those parts, and then obviously finishing off with a bit of conclusion and an introduction to alternative processes, right? So that is what we're going to look into. Now, saying that, let's go straight into a bit of understanding the audiences. Anyone here knows anything about the resistance spot welding process? Anyone is a welder, or anyone is in the welding line? Might not be able to see everyone. I've got about 92 of you guys. All right, so at least I'll just pick up the first 5 or 6 as a response to my question. We've got someone who's giving me a thumbs up, so I'm not very sure how to take that response. All right, so we got someone. Okay, yes, yes, nope. All right, so we got a yes and no, yes and no, yes. Okay, yes, a few yeses and few noses and so on. All right, yes, family. All right, I mean, I have to obviously say for those people who are saying yes to me now, all right, when I talk about welding, we have obviously welding, we've got different types of weldings, okay? We've got numerous various types of welding, but today's one will be specifically only on spot welding, all right? So that is one thing that I just want to make sure everyone understands that part, all right? All right, now saying that, let's go straight into the thing. Obviously, starting off with a bit of an introduction. All right, now everything starts with this with the history of resistance welding. All right, now resistance welding process simply is got, we use the acronym RW. So for resistance spot welding, it will be RSW. All right. Now, the resistance welding, or sometimes simply called as the electric resistance welding, is simply a process where metals are brought together, right, via the application of a pressure, and then current is conducted through this particular material. And in specific areas of these joints of the metals, you will have a high resistance created. And due to the high resistance, heat will be generated at the joint, at the area of joint, and this heat, the moment it has achieved the melting point or the melting temperature of these materials, the materials will melt, and eventually they will bond together to create a joint, right? So the whole idea in resistance welding is all about the use of pressure, the use of current flow, and the resistance to current flow, creating heat. Okay, and with the right amount of heat, if these materials can melt, you can bond them together, you can weld them together. That is what resistance welding is all about, right? Now, the person who actually invented this by I would say by accident is Mr. Elihu Thompson. Okay, so he's called the father of resistance welding. Back in the 1876, when he was kind of setting up an experiment, he actually accidentally fused 2 copper wires together, right? And as usual, he's an inventor, all right? So as every inventor will do, it kind of blinked, the light bulb kind of blinked in him to ask whether is it possible to weld metals in such a way. That means by just transmitting current through 2 metals, right? And able to fuse copper wires together. Now, in fact, that accident or incident, whichever way you take it, that was the initial discovery of welding. Okay, that's where welding, in fact, started from, right? And obviously, in the he found that is very much in the 1876 or so, about 1885, he kind of went into various experimentation and eventually brought up the concept of using transformers, right? So you got the primary circuit and secondary circuit of the transformer. The primary circuit is fitted to a main circuit. Okay, on the secondary circuit, he has actually fitted some massive copper cables, right? And the end of the copper cables were fitted to strong clamps, which kind of grasps two metal plates together. He allowed current to flow, and eventually the current flow created the resistance required for generation of heat, and the metals were joined together. That was, I would say, in fact, that is, even till now, the principle of resistance welding. All right, okay. Now, from that point onwards, obviously, he kind of created various versions of resistance welding, right? He filed up this invention of his back in the 1890, kind of filed in his invention for patent, and the RW, the resistance welding, was patented back in the 1891, right? So that is more of bit of in history. Now, when you look into the various categories of resistance welding that you'll see, right? The very first one that we're going to cover today is the resistance spot welding. So the process, the concept is the same: use of heat, the use of current, and as well as pressure, resistance to current generating heat. All right, and that heat would melt the metals together and create a bond. But it's just that all of these various resistance welding processes that you see under this category, they work differently. Okay, so when it comes to resistance spot welding, the one that we're going to talk about today, it involves the use of two copper electrodes. So you've got two copper electrodes joining the metals that needs to be welded, and then current flows, and you get the job, right? But you got also the resistance seam welding. Now, it's a variation of the standard spot welding. The only difference is in spot welding, the weld is created in a form of a spot. But if spots like this are overlapped one after another, you get the seam welding process. Okay, the seam welding process is a process widely used in production of these tin sheets, leak-tight containers, right, for fuel tanks, and so on and so forth. And then after that, you got the resistance projection welding. As you can see, the resistance projection welding, again, another form of resistance welding. This very much involves a projection. Okay, you need to have a projection like that, right? A particular projection which is raised up to a certain away from a certain surface, and then you are welded together, right? So the resistance spot welding, resistance seam welding, resistance butt welding, they work very much similar to each other. The only two differences I can see blinking. Is that because when people entering, because I can't see anything in the chat box, right? I'm just wondering what is, probably that is the notification that Barry asked me to off, I believe so, all right? Anyway, so coming back to the thing, the next two that you've got is the upset welding, or what you call it simply the butt welding, okay? The butt welding generally involves two components which have got similar cross sections. They are joined together, and this is in fact a single operation kind of a welding, right? So usually it works with wires and rods and so on. They are brought closer one after another, more like a butt to butt. I've left my camera on, guys, so you can actually see my whatever I'm showing, okay, but I might just stop that after some time. So the two different cylindrical shapes, okay, their components are brought together with similar cross sections, and then they are butt welded together in the same scenario. Both the components are pressed against each other, current flows, all right, and then melting happens, bonding happens. Okay, we call the resistance butt welding is in fact one operation process, because the pressure that is created and the current flow happens as one process, right? So that is the butt welding. And the last one is the flash butt welding. The only difference between butt welding and flash butt welding is, in flash butt welding, this is more of a two sets of operation. First, with current flowing, the pipes or the cylindrical components, they are brought together to a source to a certain distance in order to create an arc. Okay, now that arc would obviously melt the metals, and once the metals are melted, pressure is exerted in order to bring them into intimate contact so that the bond can happen, the weld can happen, right? Now, these are the various versions of the resistance welding, all right, starting from RSW, RPW, RSEW, upset welding is UW, flash welding is FW, all right? Now, but we'll concentrate on the resistance spot welding. So that's in fact the first one that Mr. Elliot Thompson have actually developed. After that onwards is back in the mid 90s and so on and so forth. That's when you got your arc welding, okay, the GMAW, the GTAW. These are all kind of bit of a newer welding processes compared to the resistance spot welding. All right. All right, now let's go straight into the process itself. Now, when you look into the resistance spot welding process, now the whole resistance welding process is a very complex process, to be honest with you, okay? It's a very complex process which pretty much involves electrical, thermal, mechanical, metallurgical, everything coupled together, all right? So it makes this whole process very, very non-linear. So that's why industry is still having issues with identifying in order to identify possible welding schedules, as well as to make sure that we are able to come with good welds. Okay, spot welds, not spot welds. Yeah. So it's a very non-linear process, and we have in the research fraternity, we've got a lot of researchers who are trying to develop modeling, okay, of this process. Well, to an extent, people manage, but there's always some level of assumption when these models are being created, because you cannot directly transfer the model to an actual process, because it's a very nonlinear problem. All right. So the spot welding usually involves a step-down transformer. You need to have a step-down transformer, like exactly what Mr. Elliot Thompson created. Okay, the primary is connected to the power line. All right, where you've got an alternating current. It depends on what's the supply that you're getting. If it's either 50 hertz or 60 hertz, whichever where you are from. All right, in Australia, we are using 50 hertz, and it's later on stepped down into a very low voltage, high amperage current in the secondary welding. Okay, that is the primary. That's the secondary. All right. Okay. So we are looking. You can clearly see that's a step down transformer, and the secondary winding is connected to two water cooled copper electrodes. The top electrode is usually moved by means of a pneumatic piston or a servo drive. It depends how the actuation can happen. Right. We do have pedestal machines which are based on pneumatics. Right. But we also got the servo-based actuation system. We also have the typical handheld type where you can simply apply the pressure manually. Right. Whichever. The lower electrodes are normally fixed if it's a pedestal type, but if it's a welding gun that is fitted to a welding robot, usually both of these electrodes, the lower electrode and the top electrode, they can move relative to each other to form to bring the metal sheets into contact. All right. Now, for the example that I've got in here, in the case for people who have not seen a spot welder before, okay, so when we press this leg pedal, all right, the secondary circuit will be completed. Current will start flowing. All right, so current would pretty much flow through the top electrode. It'll flow through the overlapping metal sheets. We got overlapping metal sheets, and then after that it'll flow through the lower electrode, and the circuit continues. So that's how the current flows in here. Typical welding current that we are looking into, obviously a bit hard to pinpoint one because it depends on the thickness of the material, depending on the material itself, but usually this can go from about 5,000 amperes, okay, 5 kilo amperes all the way up, right? So that is the typical resistance spot welding, right? Um, we do have also nowadays we use what we call as the medium frequency um, direct current welding machines, all right? Medium, in short, we call them the MFDCs, right? Now the MFDCs, the only thing in here is this is an AC current, all right? With the medium frequency direct current and using inverter technology, all right? Uh, the AC current is now been converted to direct current. Okay, so we got a DC current is being used for welding. All right, this is an AC, so we tend to have a very heating cooling kind of a cycle. Now, with the, especially now that we've gone into spot welding of aluminum materials and magnesium and stuff like that, the MFDCs are widely used, right? So with the MFDCs, what happens is obviously with the use of inverter, whatever that is being used to weld is a direct current, right? Now, it is kind of advantageous in a way because this with the use of a direct current, you can actually simply use because with the inverter the frequency is increased. So rather than the usual 60 hertz and 70 hertz, so you can have more the frequency is increased. And with an increase in frequency, with the use of DC current, we can simply weld any sort of material with with a lower current. So you don't need much of bigger transformers in here. Now that's how spot welding robots are being used. Most of the spot welding robots, they are fitted with inverter type spot welders. So we can simply generate direct current. So with the use of a direct current, you don't have the welding current going through a zero crossover, right? Because with AC, you got a positive volt polarity, negative polarity, and stuff like that. So there's always this heating and cooling. But with the DC current, it's a constant heating, right? So it's pretty much a constant heating. You don't have the cooling effect in here. Therefore, parts can be heated up very fast, right? And process can also be happening quite fast. Very limited inductive power losses with the use of a DC, and you don't have any sort of problems with magnetic materials and so on and so forth, right? So that is the now that is a process. If you look into this particular process in here, that is where the weld will be created. Now the whole spot welding, the whole component in here, we can kind of assume that to be a series of resistors. We got the top electrode, water cooled top electrode, water cooled bottom electrode. You got the metal sheets in between. All right. Now we can assume all of this to be a series of resistors. Now the resistors can be called as the bulk resistors, or they call bulk resistance, and the contact resistance. Right. Now, simply saying, since the whole process is relating to the change in resistance at this particular interface, at the fairing surfaces of the metal sheets. Now that is where you'll tend to see in a process like this, at the fairing surfaces, or at the contact point between the two metal sheets, that is where you'll see the highest resistance for current being generated, right? Let me just kind of being a lecturer at times, I like to use my pen. Now the reason in here is at the metal sheets, the surfaces are not smooth surfaces, right? You got these hills and valleys and so on and so forth, right? Obviously via the application of pressure, we'll try to bring the metal sheets into intimate contact. That means there's enough contact, but you won't be able to break this surface asperities that much. Now the surface asperities would eventually will cause the resistance to current flow. And since the resistance to current flow is quite high at the metal sheets interface, that is exactly where you'll see a high generation or a higher increase in temperature. That's what you can see, higher increase in temperature. And when you got a high increase in temperature, that will cause the heat to increase at that specific area. And with the right of with the right melting temperature. Every material has got its own melting temperature. Like steel has got 1500 degrees Celsius as its melting temperature, all right? With this aluminum 600 plus, magnesium 600 plus. So when the when the heat is created due to the resistance to current flow, when the right amount of heat has been created, melting can happen, and when melting happens, these materials can be brought together and the spot weld can be created. All right. So that is in fact where a spot weld can be created. You won't be able to create any spot welds at this context at any other point, right? Because simply on the others, especially in here, that is a water cooled copper electrode. Okay, so these areas are heavily cooled. All right, so you don't see much of an increase in temperature. You don't see much of a generation of heat. The only amount of heat that you require for this particular process is created at the interface of the metal sheets. All right, so that is the quick thing about the process. Now, obviously, what is the sequence of the process? Now that is the sequence of the process. Just to show how this whole spot welding process works, the sequence of the process is you got the top electrode, bottom electrode. Now, as I've shown a situation where the lower electrode is fixed, but the top electrode is the one that is moving, right? So the metal sheets that need to be welded, they'll be placed on the bottom electrode. The top electrode will be brought down via either pneumatic actuation or servo motor actuation, right? Now, when you apply a pressure into that, now that cycle is what we call as a squeeze cycle, right? So with the right amount of pressure, with the right amount of electrode force, the metal sheets will be brought closer to each other into intimate contact, right? Now, but as I said, even though the metal sheets are brought into intimate contact, the surface contact, they are not very smooth. So you do have surface asperities in here. Okay, to a certain extent, the surface asperities might break, but there's always the surface asperities that will cause resistance to current flow, right? Now, after that, welding current will be turned on, depending on the metal sheet, the type of material that you're welding, as well as the thickness of the material. There's a lot of other governing factors in order to determine the welding current. The moment the welding current is turned on, right, we call that the weld cycle, right? Current will start flowing. So when current starts flowing, this is where we talk about the generation of heat. The heat that we talk about here is in the form is, we call that the Joule heating. Joule heating is a heating created via resistance to current flow in a material. Okay, we call that Joule heating. So the heating in spot welding is Joule heating, right? And after that, what will happen is when the spot weld has been developed, the current will be turned off. Okay, the current will be turned off, but the electrodes will be still maintained under pressure so that the spot weld can solidify under pressure, right? Else you can have problems like expulsion and stuff like that, or cavities within the spot weld and so on. So the pressure is still maintained. Now that is what we call as the whole cycle. And then the last part is we will remove the electrodes and the metal sheets that has been welded can be taken off, right? Now that is the whole entire spot welding sequence that you'll see. And if you have seen a welding schedule, for example, like a welding schedule like this, spot welding schedule, now that's typically the information that you need to know in order to set up your spot welder, right? What's the current, right? What's the how many number of cycles? Now, as I said, if it's a 50 hertz AC spot welder, 50 hertz, all right? So you're looking into 50 cycles per second. Okay, so if we are talking about one cycle is 1 over 50, all right? So that's how you work out 1 over 50, right? So that's what, about 20 milliseconds, I believe so, right? So if you work that out over, all right, so that is about 0.02 seconds. That is about what 1, 2, 3, 20 milliseconds. 20 milliseconds per cycle. Okay, if it's 60 hertz, if you're coming from a country of 60 hertz, just divide that with 60. All right. So that is the number of cycles, and that's obviously the pressure. So that is a typical spot welding schedule that you'll come across, right? All right. Now the whole spot welding process machine involves to talk about the weldability of the spot welder. We need to always refer to what we call as a welding lobe, right? Now that's the welding lobe. The welding lobe is, or what we call as the weldability lobe, simply gives you the relationship between the weld time and the welding current for specific forces, right? The wider the weld lobe, so the wider this weld lobe is, that simply says that you got greater current range and a higher tolerance for variation in product condition. So that the welding lobe will tell you exactly the amount of current that you can use, right? Now, anything below that, we are looking into a situation where there may not be any sort of spot welds created. Either it's a zero fusion condition, okay, the combination of force, current, as well as time is not sufficient to create to heat up the interface to create a spot weld, right? Or it can be a very small spot weld, undersized weld we call it, right? Anything above that, this over here, now that is where you'll tend to see expulsion, right? This is mainly due to overheating, the use of high current, right? Or due to the use of high welding time or a lower electrode. So either one of these, yeah. So generally, that is how the spot weld lobe has been created. All right. Now, now that is a typical example of a spot welding. All right. So that's a nice animation for you to see, right? That is a spot weld. So the whole idea of the spot weld is, right, we will normally do a spot weld and we will section it. So the actual spot weld is actually made out of three different regions. You got the fusion zone. Now that is where the weld is actually being created. Now the weld is obviously created via rapid heating and cooling. All right. So the microstructure here is very much columnar size kind of a microstructure. It's a very coarse kind of a microstructure. Usually it's either austenite or martensite, right, depending on how it was cooled. And then you got the heat affected zone over there, all right, where the heat affected zone does not undergo much of melting. Okay, there's not much of a change of microstructural changes happening in there, and that is the base metal. So that's how we. And if ever we want to talk about the length or the diameter, if you want to check out the diameter of the spot weld, we'll normally measure the spot weld diameter from that point to that point. So the two longitudinal lengths of the weld is what we. Now you might not be able to get this in an actual production. All right, this is very much a research kind of a thing where we can section it and so on. In a production area, we want to measure the diameter of the spot weld. We'll normally do a chisel test. All right, we'll normally do a chisel test or peel test, and then we'll break it up, and then we'll measure the diameter using micrometers or whatever like that. This is more what you tend to see in a research scenario, right? All right. Now, there are two things that determines the quality of a spot weld. Okay, the diameter as well as the joint strength. Okay? Whenever we talk about joint strength, is how the spot weld has to fail. Spot welds typically fails via two ways. It can either fail via what we call as a pull-out failure. Now, pull-out failure is like what you see in here. Two metal sheets bonded together, and when they are pulled apart, the weld will break away from one metal sheet and stick to the other metal sheet. Now that's what we call as a pull-out failure, right? Now the pull-out failure usually happens due to a very extreme plastic deformation, right, of the metal. Okay, due to the extreme plastic deformation, you'll tend to see the pull-out failure. Now, the other one that you will come across is what we call as the interfacial failure. Now, the interfacial failure is a failure that happened at the interface of the two metal sheets, the interfacial failure. Now, when it comes to automotive industry, the requirements of a spot weld to identify whether a spot weld is of a good quality is on how it fails. And the required, based on the standards, the requirements for spot welds is via pull-out failure. Now, because the pull-out failure is a type of failure where it was found that it's able to absorb a huge amount of energy before failure. So the spot weld is quite strong and is able to absorb a huge amount of energy before it fails, right? It's way stronger compared to an interfacial failure. So that is the. Now, there are some standards, right? For example, the welding standards like NC, AWS, American Welding Society, and so on. They have actually created the weld diameter that's required in order to achieve a pull-out failure should be equals to 4 square root of T. Okay. Now, this is a common welding criterion that we are using in automotive industry. There are some variations to this also. JIS, Japanese industry of standards, they use D equals to 5 square root of T, right? So this is 5 square root of T rather than 4 square root of T. There's some slight differences in this variation, right? So that's what you would have seen even in here, in the weld loop. The general point is about 4 square root of T. T is the of the metal sheets, right? Added up together. We got some which is 5 square root of T. This is the typical areas where we'll assume that the weld is of a good quality. But the only minus point of this welding criterion is, especially at this particular moment in time when we are dealing with all these advanced materials, is this criterion does not take into account the microstructural changes that happens in materials when you are welding the materials. So this is purely only on thicknesses, welding metal sheet thicknesses. It worked fine. It worked fine for the days when we were doing carbon steel, mild steel, and stuff like that. But now that this welding criterion might be quite redundant, especially then when we are looking into welding aluminium and so on and so forth. That might not work anymore, right? People who have done research and so on, they have actually brought up a more detailed type of welding criterion, right? So apart from this one, which just referring to thicknesses, now we are using one with thicknesses as well as taking into consideration the weld's ultimate tensile strength as well as the shear stress that's related. Because in here, there are two forces that are working together with each other, right? We got the tensile force as well as the shear force. For example, this is work that I've done recently myself, right? In order to test welds, apart from the usual chisel test that industry does, if you go into more on the actual analysis of the spot weld fracture, the typical fracture of spot welds ideally happens due to two different forces. You got the shear force as well as the tensile force, because it was actually found that when in an actual scenario, when the spot welds are being used in automotive bodies, they will be subjected to shear force, bending force or rotational force, all right, plus tensile force. So we have got different testing methods to test all these different types of forces, right? The tensile force, the shear tensile force, that setup is what commonly used in order to identify the strength of a spot weld. That works under tensile force, tensile stress. We've got this one more of a peel test. This looks into the bending force or the bending moment at which the spot weld has been subjected to. Now that is more of a normal shear stress, right? It was found that each one of these welds each one of these tests gives you different types of information regarding the strength of the weld. So that's exactly what I meant a while ago. Spot welding is a very hard thing to look into, but generally that's how we can actually categorize the welds, right? All right. Now, since time is moving on, but this is typically looking into how the whole weld size varies with increase in current, right? With increase in weld time or with increase in force, you'll tend to see variation in the weld diameter, okay, as well as variation in the weld strength, right? All right. There's also other factors involved which affects weld: electrode indentation, electrode wear, right? Oxide buildup, poor fit-up, that means the metal sheets are not placed properly. The spot weld position, no, the spot welds cannot be welded very close to each other. They have got something called shunting effect, right? So that will also affect the spot weld quality as well as the heat balance, right? Now, these are typical concept of that affects the quality of the spot weld. All right, now let's go straight into the industry itself now, right? So if you go into the industry, spot welding is one of the primary welding process that are being used at the moment. Right? Simply saying, each body in white uses about 2,000 to about 5,000 spot welds, right? So that's the amount of different types of spot weld that you got in here. I don't know whether it works, but that typically gives you a rough idea of how this welding has been created, right? All right. Anyway, just to show you how that happens. Now, the whole idea here is the vehicle crashworthiness, which is defined as the capability of the car structure to provide adequate protection to passengers, largely depends on the integrity of the integrity as well as the mechanical performance of the spot welds. Okay, the spot welds, they play a huge role because the force transfer within the structure of the car is transferred through the spot welds, right? They are the spot welds are the one that kind of transfers the load during any sort of crash, automotive crashes or whatever. And furthermore, they are the areas where the spot weld acts as fall initiation sites. So when the metal sheets fold up each other, when they crumple, right? They crumple at the spot weld area. Therefore, that area will be able to absorb all the impact energy. For example, if we look into this one, all right, these typical areas is where you'll tend to see a lot of this impact energy is being required. The front part, the frontal area, the back, rear, as well as the areas where you got the B pillar and the A pillar and so on. So these are typical areas which are meant to be very important in terms of making sure the crash worthiness of the vehicle is maintained, right? So saying that, obviously now material selection comes a very important part in automotive industry, right? It's a key when it comes to vehicle design. Material selection is obviously a key component. There are a lot of various factors that are involved in driving material selection in automotive industry. As I mentioned, safety, fuel efficiency, manufacturability, quality, and obviously not importantly the cost. So there's a lot of things that's happening at the moment, and that in order to achieve this, the body in white, this is what we call as body in white of automotives, right? The body in white are being looked into in terms of manufacturing, where we are trying to see whether we can use different types of materials, right? For example, if you look into here, in the olden days, we were just looking into wood and steel and so on. Things has passed over time. We are seeing a lot of different types of materials coming into the market, right? Coming into use. We've got the advanced high strength steel, we got the aluminum, we got the magnesium, and so on and so forth, right? Now the question now is, these are just some examples. You can have a look at this by yourself later. The question is, why are we looking into material design, multi-material design, right? These are typical scenario reasons. The weight reduction. With the weight reduction, we can improve fuel economy, right? For example, for electrical vehicles, EVs, right? It was found that you can increase the driving range by reducing the weight of the weight of the car. So you can reduce the weight of the car. You can in fact increase the driving range, right? Because of the by increasing the amount of current that we are using. Obviously, CO2 emission can be reduced. So reduction of CO2 to a certain extent. And now this is only for automotive, but when you go into aircrafts and so on, it was also found that by using composite materials in aircrafts, we can actually obviously minimize a lot of CO2 emission. So that is typically the whole important point. Weight reduction for the sake of CO2 emission, weight reduction for the sake of fuel consumption, fuel efficiency, right? But there's another important point also. How about safety? Now, obviously, that's where the other part of it is. So if you look into a material like this, safety is also another important. It's not about just trying to reduce the weight of the car, but also trying to make sure at the same time trying to make sure you are building a safer car. All right. So if you look into the BiW of a car, there are two specific areas: the crumple zone. Now, the crumple zone is the zone where, due to frontal impacts and so on, the shock that's been created, they have to be slowed down so that the energy is not transferred to the passengers. Now, with materials like AHSS and so on and so forth, we can obviously build a more stronger structures in this area in order to reduce, in order to kind of make sure that the shock that has been created due to impact is transferred very slowly, right? On this side, we got the safety cage. For example, there's your B pillar, A pillar, and so on. Now, this components, they should not buckle. So again, we need a very strong material to make sure that these areas are quite safe enough. We have been doing this with at the moment by having 2 or 3 different materials spot welded together. But when you spot weld 2 or 3 materials together, it's increasing the weight of the car, right? So in order to minimize this, that is where we look into the materials. We've got the currently introduced one is the AHSS, the Advanced High Strength Steel Materials, right? These are the current generation of steels that we are currently using. They are kind of very strong, but at the same time they are quite ductile, right? We used to be using low carbon steel in the older days, and then slowly we went into more of the conventional high strength steels. Nowadays we are going into the advanced high strength steels, right? We've got the first generation, second generation. In fact, we got the third generation that's currently being looked into, all these various types of materials. Now, what is the challenges with these kind of materials is when it comes to spot welding? That's the thing that I'm trying to bring up now. Advanced high strength steel materials. These materials, they are no doubt they are quite strong, but the thing with them is they have been engineered in such a way that a lot of alloy has been put into this, right? So to make this this whole strength, whole steel to become stronger, we have added a lot of alloying in it, right? carbon plus various types of alloys. So the steels are quite strong. But the problem with this one is when you weld them together, okay, when you weld this together, they'll end up creating martensite within the weld, right? Now, high strength steels, no doubt they are quite strong, but they will never give you a pull-out failure. As I mentioned a while ago, the spot weld requirement in automotive industry is you need to get a pull-out failure. That means the weld nugget should be pulled out from one part of the steel, but on the other steel it should be sticking. That's the pull-out failure, which typically shows that the spot weld is able to absorb a lot of energy. In advanced high-strength steels, no matter how strong the weld is, it will crack via interfacial failure, because the whole via due to welding, because of the use of heat and so on, the whole structure, the whole weld will be martensite. Now, when you talk about martensite, is if anyone knows about martensite is a microstructure that is always hard and brittle. Okay, so these welds, they will naturally break. They will naturally break. All right, guys, I'm almost coming to the session. I'm not sure how this goes. My apologies. I might have to go beat about 5-10 minutes if it's fine. Okay, or else this is recorded. You guys can view that later. All right. But let's. My apologies. Might have to overshoot by about 10-15 minutes, but almost coming to the end of the session. Yeah. All right. But anyway, going back to what I was discussing a while ago, with advanced high-strength steel, because of their natural ability to form martensite, this particular material they will always break via interfacial failure. All right, and on top of that, most of the steels nowadays they are normally coated with zinc in order to prevent corrosion and so on. When this particular zinc it melts due to high heat, when it melts, it'll start penetrating through the grain boundaries, and this will give another scenario, in another situation, which is called the zinc induced liquid metal embrittlement. Okay, the whole entire weld can crack easily. Now that is a scenario that we are actually looking into at the moment with this advanced high strength steels. To be honest with you, resistance spot welding may not be the best candidate for the materials from this point onwards. Now that's why we are going into more of the solid state welding, all right, like friction stir spot welding and so on and so forth. But what I'm trying to show you here is we can still use resistance spot welding for these materials with a bit of slight variation in the process, right? Now, the most common practice that industries are doing at the moment is they are using multi-pass currents. So the typical weld schedule will only have a single current pulse, right, which goes for a certain time. But nowadays we are using two different what we call as a double pulse heating. Okay, the actual welding current is there, and then you got a quenching session, quenching time, or cooling time, and then another current. We call these the tempering current. Now the tempering current is actually used to soften the spot weld, right? Now we'll tend to see these a lot of heat treatment. In heat treatment, whenever a particular material is heated up, it'll be quite hard and strong. So in order to soften it, we'll do tempering. Now that's exactly what's happening in here. All right, by using double pulse, or even some uses triple pulse. All right, the whole idea here is to soften the spot weld. That means to reduce down the intensity of the martensite. Now with that, it was found that we can still spot weld the AHSS materials easily, even though naturally they are quite brittle. But with something like this, with the use of a multi-pulse, we can easily weld all the various types of AHSs we got. We got the DPs, we got the CPs, and so on, which can easily weld them easily. Right? Now, has not really been looked into as part of the actual production, but in research, there are a lot of research being carried out. Right? Some of the two ways where the advanced steels can be spot welded was found by having something called an interlayer. That means in between the metal sheet that you're welding, you place a separate steel. All right. We call this the interlayers. In fact, that the same method is being used even in aluminum as well as magnesium. All right. With the use of an interlayer in between, it was found that the microstructure, the whole idea here is modifying the microstructure. So the microstructure can be modified in such a way that the weld has got a reduced martensite contents, more of an austenite content. Therefore, you are able to make the weld more stronger and ductile rather than strong and brittle. Okay. So we got the interlayer, and we got another one which is called the magnetically assisted. This one is using magnetic magnets in order to manipulate the liquid current, right, of the weld pool. Some ideas that are being looked into at the moment. But in terms of actual manufacturing usage, most of the time we are using the pulse resistance spot welding, right? Now that is on advanced advanced high strength steels. So the advanced high strength steels are steels which have got yield strength anything greater than 550 megapascals. So the issue with this is because they are highly alloyed, they've got a very high carbon content. When you heat them up, they become hard and brittle. So they don't give you the required pull-out weld. Even though they're strong, they will naturally fail via interfacial failure. Right? Now let's go into the aluminum and magnesium. If you look into the aluminum and magnesium, that is another totally different story. All right. With the aluminum as well as magnesium, the important point in here is both of these materials, they've got a very high thermal conductivity compared to steel. Okay. Aluminum is about 3 times in terms of thermal conductivity, 4 times of electrical conductivity, right? And they need a huge amount of current. So if you look into the aluminum itself, aluminum requires about 3 times higher current, 3 times higher current happening at a 1/3 of the weld time that we use for steel, right? So that is for aluminum. The same scenario happens for magnesium. Even magnesium is the same thing. Magnesium's current usage is quite high. Now, both of these materials, aluminum and magnesium, they are still in a very infant stage of usage, I have to say. Aluminum, at least to an extent, we have actually got used to it, right? Of spot welding aluminum. But magnesium is still new. The whole thing is we got magnesium. We had a magnesium vision 2020, where we were assuming by the year 2020, at least the average magnesium usage in cars should be of that much, right? But to be honest with you, this particular vision was not achieved because magnesium has got a lot of other issues, plus the cost. Okay, plus the cost. So the problem with magnesium and aluminum is when you weld them, they create, again, all of these are very much microstructural in nature, right? If the AHSS, you can they are having problem with spot welding is because of the formation of the martensite, which is hard and brittle. In the aluminum as well as the magnesium, when you weld aluminum with steel or magnesium with steel or magnesium with aluminum, what happens in here is obviously welding magnesium with steel is a challenge because of the huge difference between their properties. Aluminum to steel to an extent you can weld by using direct current, right? But the problem in here is in both of this, we have got something called an intermetallic compound produced at the sheet interface. So that is simply the microstructure. So that is aluminium and that is steel. And what you'll notice is because of the heat transfer that's happening, there is an intermetallic compound that is formed. Those people who are quite familiar with alloys, you'll understand alloys and intermetallic compounds. Okay, intermetallic compound, they've got a very important behavior. They are hard and brittle. Okay, so that is the problem with aluminium as well as magnesium. When you weld them together, they create this intermediate layer, which we call as the intermetallic compound, in short IMC. The IMCs, they are very hard and brittle. So again, when you pull the metal sheets together, they can break easily. No doubt they are light and weight, but as you can see now is with spot welding, because spot welding is typically using material, okay, the heating of material changes the microstructure. When it changes the microstructure, you're going to have issues like this, right? On top of that, magnesium as well as aluminium, when you weld them together, they form oxide layers, and these oxide layers can easily stick to the welding electrodes. Again, that is another issue. Okay, they will reduce the life of the electrode. Aluminium, obviously not that much, but magnesium is quite bad in that extent, because when you weld it, it'll stick to the metal sheet. It'll stick the copper electrode can easily stick to magnesium, okay, creating damages to the electrode. So these are the typical problems that we are seeing now with resistance spot welding with welding magnesium as well as aluminium. All right. All right. Now, how do we improve this? There are some ways. The most common one that we are doing at the moment is we are using, as I mentioned a while ago, we are using direct current. Now, with the direct current, you can supply current, a high current, at a very short time. Now, the thing with magnesium and aluminium is they are very good thermal conductors. They don't capture heat easily. Okay, since they don't capture heat easily, they don't melt. But if you can weld it at a faster rate with using a high current at a very short time, then you can weld these two metal sheets together. Okay. And direct current can do that because direct current don't have the heating and cooling cycle, so you can easily weld them. But on top of that, some that are still being looked into, some still have not really gone into proper industrial application, some that are within the research kind of area is using different types of electrodes. For example, if you look into welding alloy aluminium with steel or magnesium with steel, we'll tend to use domed electrode for magnesium, or this kind of a ring electrode for aluminium, and a flat nose type of thing for steel, because the cross section of the electrode will define the current density that's coming in. All right. So if we are using a dome type, the cross section of the electrode is quite small, so the density of current is quite high in a smaller area. The flat electrodes, my apologies, the flat electrode, they got a greater area, so therefore the density of current will be lesser on the steel side. Now this will create a heat balance. Okay. The problem with spot welding all the while, even before this, is of welding materials with different thicknesses. Okay, creating a proper heat balance has always been a challenge in this, especially now with different materials. That's also another issue. So by using different electrodes, different contour of electrodes, we can actually create spot weld. That is something that's being looked into. Another common process, another common modification that is being researched, not really gone into practice yet, is the use of steel interlayers or inserts and stuff like that. Okay. Now there may be an issue with this because in at the moment what we are looking into is we are trying to reduce the weightage. That means we are trying to go into more lighter welds, right? My apologies, not lighter welds, lighter materials. But this kind of modification, they are trying to introduce new materials in between steel and aluminum, steel and magnesium, for example, in order to modify the microstructure. This means we are simply adding a new steel in between these two. Now, it might be able to spot weld both of these materials together. But the question now is, would adding extra steel or extra inserts like this, which are different, an extra material, how would this affect the whole entire MMD design? Now, that's always a question mark, right? But it was found by using this kind of third elements, we can easily weld this kind of materials, right? And for the moment, we are also looking into hybrid welding, spot welding with adhesives together. There has been some success story, but again, this might be a situation where it might increase the production time because you need to add on adhesives before you do the spot weld, right? All right, guys. Now the last one for today is joining polymer composites. Now this is in fact the hardest of all the three, right? The AHSS, the advanced high strength steels, they are already steels. Okay, they are fine. They are conductive materials. The aluminum and the magnesium, they are material. They are metals. They are conductive in nature. All right. The issue now is welding a conductive material with a non-conductive material. For example, polymer-based composites. Okay. Now, this is a huge challenge, and in fact, it is an area which is kind of newly researched at the moment. Not much of a success stories that has came up, but there are a lot of possibilities of being able where we can able to weld steel with polymer. Okay. Now there are a lot of areas in here, but typically how this simply works in all of this is heat is being created on the steel. So that means via the current is being allowed to flow with electrodes placed in series or a slight design on the electrode like this, or by inserting a special element, right? Current actually flows on the steel. So when current flows on the steel is heated up. Okay. Now the heat from the steel will later on will be conducted into the polymer. So that means the polymer is not directly welded, right? The current does not directly flow through the polymer. The current is flowing through the steel. The steel is heated up. For example, in here, the steel is heated up. Even in here, the metal is heated up. Even in here, the metal is heated up. Even in here, the same thing. Okay, this is shunting. Okay, metal is heated up, and the heat from the metal flows through the polymer because polymers has got a very low melting temperature, right? If you directly transfer current into polymer might have melted and vaporized by the time steel undergoes melting. Okay, so what is happening now is we are trying to make sure that the metal is heated up and the heat is being conducted from the metal to the polymer to melt the polymer, and therefore both of these will bond together via a diffusion process. It's not actually a actual welding. It's more of a diffusion. Okay, just like adhesive bonding is a diffusion. All right. Obviously, not still under research. A lot of work is being looked into, but this is something might eventually end up being a huge player in the automotive design when polymers are brought into composites are being looked into more in the body in white design. Right. All right, guys. So with that, let's go finish off with the conclusion. My apologies, might have dragged this a bit higher. Okay, but then let's finish this off. The conclusion pretty much is resistance spot welding is obviously a main welding process in the automotive industry. Ever since the days welding was introduced, resistance spot welding has been widely used in automotive industry simply because process-wise is very simple. Okay, it's a very simple process. It can be easily automated. All right. And third thing is, unlike the arc welding, you don't have to use separate materials like filler metals, all right, and so on and so forth. It's a simple welding process. But with the introduction of the new materials like this, the resistance welding is obviously having a challenging situation, because resistance welding by nature, you need to have it's very much a fusion welding, which depends on resistance of current. But materials like polymer, materials like aluminum and so on, when you weld them, first thing, polymers, you can't weld them because they're non-conductive. Steel, aluminum and so on, the microstructure that they create may not be very favorable for the spot weld criteria that has been created in the industry. So there are a lot of challenges like that. So what's happening now is the conventional resistance spot welding has been converted into more of a hybrid type. So from now onwards, if you see spot welding, most of the time this might be a hybrid version of a spot welder. For example, like what I've just add on in there, you got something called friction stir spot welder. Okay, ultrasonic spot welding. Now, ultrasonic spot welding as well as friction stir spot welding, both of these don't come under fusion welding. They come under solid state welding. So simply, they don't heat up the metal. Okay, they don't heat up the metal. And the last one is the laser spot welding. Laser spot welding is very much similar to resistance spot welding. It's a fusion base, but then it uses laser, right, rather than heating up the metal. So slightly different in terms of its working property. All right, guys. So with that, I think we have already come to the end. So this is a bit on introduction to the resistance spot welding, as well as the challenges that this particular process is undergoing at the moment when we are dealing with various types of new materials that we are currently using in automotive design. Right. Okay, with that, I'll finish off my webinar for today, everyone. And if there's any questions, I think we can still have probably about 5 minutes for any question and answer. Thanks, guys. Thank you. Apologies for the thing. Now, underwater welding, resistance spot welding is not the right thing, Praveen. When it comes to underwater welding, it is still the arc welding. Resistance spot welding is not you cannot put it underwater. Okay, it doesn't easily do underwater welding. So you still have to stick to arc welding for that. Okay. All right. Any other questions? All right. I've been seeing some people talking about. Now, I am planning to have another webinar on friction stir spot welding, as I was saying. All right, but not so soon, guys. Probably in September, October. All right, because I'm currently writing up a paper on friction stir spot welding as well as ultrasonic spot welding. Once I finish that paper, once I publish the paper, I would obviously this might be the first series within series of webinars that I'm planning. This would be the pretty much the first of in that series. Please, there might be another series of webinar coming probably in October or November. I can't promise when, but it'll surely come, where I'll deal a bit more on the friction stir spot welding, all right, as well as ultrasonic welding. All right, what is the difference between solid metal arc welding and resistance seam welding? Simple, Gerfried. Arc welding and seam welding, they are both comes under fusion welding. That is their similarities. The difference is arc welding uses arc. Okay, it uses pretty much an arc to create heating. Seam welding, spot welding, all the rest of the other welds that I've just mentioned today, they work under resistance. That's where the keyword is resistance. The heat is being generated via resistance to current flow, right? In arc welding, the heat is created via formation of arc. All right, I think we should be done now, everyone. Barry, you want to take over and finish up this?
Yeah, thank you, Dr. Arvin. Thanks everyone for joining. So this slide is just to see our upcoming courses. So if you can just, if you would like to read more, just go on our website and course schedule. So you'll be able to see our upcoming courses. And yeah, our upcoming webinar is it's going to be next week, Friday on the 1st of June. Yeah, so for you to be able to join the session, you just have to sign up and then you are good to go. And then just for those who have been asking about the certificate of attendance. So if you can just scan the QR code, and then obviously it will lead you to a short survey form that you need to complete. If you're unable to scan the QR code, I just posted a link, so you can just make use of that link to complete the form. Yeah, just note that the PDF together with the recording will be provided to you via email. So just check your email after 2 working days. So yeah, just also check under junk or spam folder as well. Yeah, I think that's about it. And then feel free to reach out if you have any suggestion, if you have any feedback. So you can just make use of the following email, webinar@eit.edu.au. Just give us your feedback or any suggestion. We would love to hear them. I think that's it for today. Thanks, Dr. Arvin. Thanks, everyone,
Thanks,
for
Barry.
joining.
Thank you.
All right. Thanks. Cheers. Have a great day further then.